Hi guys, good afternoon. Good afternoon, guys. Hello, hello. I hope all you can hear me. Hello, hello. You hear me? Okay, perfect. Yeah, I wanted to make sure that you're able to hear. Good afternoon. Good afternoon. Excellent. All right, so I think this is all we are going to get today. 8 people, 7 people actually. That's all right. So, as you know, today, meaning tomorrow, you are going to be doing a synthesis of cinnamaldehyde. By the way, how did the lab go last week? It went well? Last week's lab went well? Anyone? Comment? Pretty good? That's good, Amira? It was long, yeah. That was kind of understood. It was going to be long. So it happens few labs are a little long and many labs are even shorter. That's you know that this is how lab goes. Always is the case. All right, so now we have 8. Oscar left. Maybe he will join back. Uh, okay, Danny, try to rejoin. That's good. Yeah, some days are better than others when it comes to Blackboard. We all know that Blackboard is pretty unstable occasionally, if not often. Right? That may be the reason Oscar and Danny, two of them, are trying to reconnect. Okay. I wait another minute. So, despite being long, was it what you expected, or was there any undesirable or unexpected surprises? Anything? No? So all in all, it was okay, right? It was as expected. Very good, Anastasia. That's perfect. Glad to hear that. Uh, okay, good. Yeah, Danny is back. Oscar may be trying to get back also. I don't know. Good news on my side, I don't hear any noise, so it's very quiet here. So it should be good. All right, so today's discussion is not going to be long, so therefore, time-wise, you're also fine. No worries. So as you know, tomorrow's lab being a synthesis of cinnamaldehyde, that means you are going to have cinnamaldehyde retrieved or saved from 3 different methods, 2 different extractions, and the synthesis you do tomorrow. And that samples you will analyze the following week. So following week analysis uh, should be simple in the sense NMR takes only seconds or no more than a minute to take it in the lab. You may want to ask the TA to give you a better NMR uh, spectrum, because the one that you get from the lab actually is not very good quality. I checked one day that NMR looked pretty miserable. It hardly looked like an NMR spectrum. Certainly, you do not see all the multiplicities clearly at all. So that's bad news. So in the past, what you used to do, we still cannot have you take individually in a 400 megahertz NMR, because 400 NMR megahertz is only used by the experts. They are not for undergraduate students use. So only you could get a spectrum or watch the NMR manager take a spectrum, or TAs know how to do that. They can also take a spectrum. I would suggest, maybe I'll send an email to Alexi, that perhaps even though you take this low resolution NMR in the lab, they do take you in the 400 NMR machine, and they will take NMR. You will just watch. Even if you just watch, that is still going to be more satisfying, and you will get one spectrum that will be really good spectrum. So I'll make a point to ask the TAs. You could also equally tell the TAs, and TAs are very nice. So tell them that professor said that if you could take us to the 400 megahertz NMR machine room, and you guys take it, one person, even one sample, we will have a better feel for the big NMR machine. But the one that is in the lab, you will be able to do that. It's very bad resolution. That is not going to be very satisfying, but at least you get a direct touch with machine. But 400 megahertz, you will not take yourself. They will take, you will watch from standing 6 feet away, practically. Yeah, because that room, NMR, the magnet being highly powerful, you have to stand a little further, etc. Anyhow, so going back to the other aspect is that the following week you will have the midterm. I had sent you the announcement. So you will come to Marshak 117 on October, was it 25? It's probably 25th, right? Today is, yeah, you will come there on Tuesday, and that is 25th. Yes, exactly. Because you do not need to come on Monday, which also would mean Monday I don't know, maybe I can still, no, whatever I need to talk, we have talked already. We discussed GCMS, so which means next Monday we do not need to meet because we are going to have the midterm on Tuesday. So next Monday we do not have to meet on Zoom. I mean on Blackboard. That's what I meant, right? So that is kind of understood in that sense. All right, so coming back to our lab, the one you are going to be doing today is synthesizing cinnamaldehyde, which is your model molecule this semester, because you are extracted, isolated from two different ways. Now we are going to make it. But you're not going to make it from very many steps of reactions. You actually do a one-step reaction. So reaction is going to start from corresponding alcohol. To make cinnamaldehyde, you make from cinnamyl alcohol. And as you know that your cinnamaldehyde is also called trans-cinnamaldehyde. So the structure is going to be trans in both cases. So I'm going to draw it now here. So your cinnamyl alcohol would have the benzene ring, and this vinyl carbon, that position is trans, as you can see, trans. So this time you start from corresponding alcohol, CH2OH. It is trans because two hydrogens are opposite direction, therefore it is trans. And then you are going to be making, from there you make corresponding, I might as well write it here, the name trans-cinnamaldehyde alcohol, and you will make trans-cinnamaldehyde. The structure will be very similar to that. Here you will have the aldehyde group. It will be CHO. CHO. Right? You are familiar with the aldehyde group, writing CHO, you understand it is carbon oxygen double bond and carbon hydrogen single bond. So what do you see in terms of functional group transformation? Here an alcohol functional group is turning into corresponding aldehyde functional group. Now, can anyone tell very quickly, is it an oxidation or a reduction? What kind of reaction does it look like? Alcohol turning to aldehyde is oxidation or reduction? That should be fast answer. Okay. Thanks God, you changed your mind. Oxidation, not reduction. It is oxidation, right? Remember, the organic oxidation means increase in oxygen content or decrease in hydrogen content. If you look at this structure, your hydrogen is less, right? Oxygen remaining the same, but hydrogen is less in the product. So generally, alcohol to aldehyde is oxidation. And if you do further oxidation, you get carboxylic acid, right? That is the highest oxidation state for organic functional group. And you are not making that, you are only making an 1-degree alcohol to an aldehyde functional group. So here is your trans-cinnamaldehyde. So now that you already mentioned it is an oxidation, what question comes from after that? If you're an oxidation, question is, what is the oxidizing agent, right? To carry out an oxidation, you need an oxidizing agent. Oxidation. So what kind of oxidizing agent would do this job? Our reactant is this is 1-degree alcohol, and this is becoming an aldehyde functional group. Aldehyde. So that's why it is oxidation. So oxidation requires oxidizing agent, but what kind of oxidizing agent should you choose? Well, as you have learned in organic 2, the strong oxidizing agent converts an 1-degree alcohol to carboxylic acid, not an aldehyde. Only a very specialized weak oxidizing agent would stop it at the aldehyde stage. So you should always keep note of all the oxidizing agents, reducing agents. Not only that, which one is stronger, which one is weaker. These things are kind of tools in your toolbox as an organic chemist. So for example, now that we are going to have time, I might as well indicate some of the strong oxidizing agent. Strong oxidizing agents are, number 1 was potassium permanganate, right? KMnO4. And very similar to that was chromic acid, H2CrO4. Chromic acid usually comes as, this thing comes as sodium dichromate and sulfuric acid, or potassium dichromate and sulfuric acid. Na2Cr2O7 plus sulfuric acid, that gives you chromic acid. But the actual species is chromic acid, H2CrO4. Or it can be corresponding potassium K2Cr2O7 plus sulfuric acid. So these are the thing. Now, these are being strong oxidizing agents. They oxidize all the way to carboxylic acid. That's why we cannot use it. However, if you recall our discussion in lectures, some of you, those who took with me, when potassium permanganate oxidizes and anything it oxidizes, it has to be reduced itself. So what is the reduction product? Reduction product, if you remember, it is actually manganese dioxide. So potassium permanganate is reduced. It is an oxidizing agent. As you know, oxidizing agent always itself gets reduced. So it is reduced to manganese dioxide. If we inspect their oxidizing ability based on their oxidation state, here we quickly go back to GenChem 1. Oxidation state of manganese in potassium permanganate would be what? Can you calculate quickly? Potassium is 1 plus, oxygen 2 minus. That gives manganese to be, oxidation state is going to be 7, right? Plus 7 oxidation state. In manganese dioxide, that becomes 4. So as you know, oxidation is also a reaction in which there is a decrease in oxidation number that you learned in Gen Chem 1. Now, even though this is the reduced state of manganese, it can still be further reduced, meaning it can turn into manganese in oxidation state 2 when it becomes Mn or manganese hydroxide. Oops. To hydroxyl group. As you can do the calculation, that will have oxidation state of 2, which means manganese dioxide can still act as an oxidizing agent. While potassium permanganate is a strong oxidizing agent, manganese dioxide can act as a weak oxidizing agent. And as a matter of fact, that is what you are going to be using. Your procedure is made in that way. You'll be using manganese dioxide as an oxidizing agent because we are only oxidizing 1 degree alcohol to aldehyde, not all the way to carboxylic acid. Now, just a quick a reminder or review of weak oxidizing agents. Weak oxidizing agents. What are some of the weak oxidizing agents that you have used before? Do you recall any of those? One of them used PCC. Recall that PCC was most commonly used in the lecture classes. PCC was, what was the PCC structure? Pyridinium chlorochromate. Now we are in an advanced organic class. You need to know their structure. It's a pyridine molecule, which was one of those aromatic compound that has lone pair of electron, but that actually can be protonated by HCl, becomes pyridinium ion, and you have chromium trioxide and Cl minus. This is PCC, called pyridinium chlorochromate. I probably don't need to write that, but I might as well. Pyridinium chlorochromate. Okay, so that is one of them. And likewise, you had used a number of them. There was another, was the Swern oxidation you learned in organic 1, right? Swern oxidation. And a Swern oxidation reagent was a simple reagent, 2 chemicals. One is, what is it called? DMSO. It's a solvent, DMSO, and oxalyl dichloride, COCl2, right? Is the from oxalic acid, oxalyl dichloride. That was one used. And now we are adding in our list the new one, manganese dioxide. This is what we are also going to be using. As a matter of fact, that is the one you will use. So that's the weak oxidizing agent. There are a few other weak oxidizing agents if you recall, we learned in carbohydrate chapter. Carbohydrate chapter, you have seen the bromine water oxidation. That doesn't oxidize alcohol though. That's slightly different in carbohydrate chapter. Bromine water, molecular bromine and water oxidizes an aldehyde group to a carboxylic acid group, right? That is bromine water. And very similar to that, you had nitric acid oxidation, right? That you did, both of this you had did in carbohydrate chemistry. So that's that. So as I mentioned, in our case, we are going to be using this manganese dioxide, MnO2. Okay, so that's that. So if you do the oxidation, you get this product, you will separate them and you will analyze doing GCMS and possibly NMR. And definitely you will test or check with TLC, that as we have seen becoming a tool you use with every experiment when you have a product. All right. So now As usual, our next question is how this reaction occurs, or in other words, the reaction mechanism. So let me write you the reaction mechanism, how it occurs. So starting with, actually it's not a whole lot of drawing. You can quickly draw that benzene ring, and you have this carbon-carbon double bond. It's not a huge amount of drawing, right? CH2OH. So don't feel lazy. You can just quickly draw it. Reacts with manganese dioxide. Manganese dioxide structure is like this. Manganese double bonded to two oxygens, and then what it does is this alcohol's oxygen makes a bond with manganese. Manganese to oxygen bond breaks. That gives you corresponding structure like this. Here you have this CH2 OH, and I might as well write that O and H right downward. Easier. And it made a bond with manganese that has one oxygen double bonded, one oxygen single bonded. Oxygen is minus. Manganese 4 bonds still here, so that is fine. Oxygen has become oxygen plus. By the way, mix up this. Okay. So that's that. And then from there, you do an internal proton transfer, or IPT. We had used this few times in lecture. I don't remember when I used in the lab, but you know the mechanism, internal proton transfer. So what it actually does is one of this hydrogen from oxygen transfers onto this oxygen. That's what is internal proton transfer is. So when you do that, that is turning into this. Here you have this CH2O, and let me write this CH2 little bit differently because we want to show the mechanism. So let's write the hydrogen, one hydrogen up, another hydrogen down, and this oxygen we are writing like, let's write like this, oxygen making a bond with manganese, and that has manganese to oxygen double bond, and of course another oxygen picked up the hydrogen, became OH, right? Because we did the internal proton transfer. Proton from oxygen has gone to the oxygen on the right hand side, so that became OH. So from here something unusual happens. Unusual in the sense, for space purpose I write the IPT on this side. IPT and a little bit of space for the arrows. From this, it undergoes a little bit crazy reaction. It goes into a radical mechanism. Manganese to oxygen double pi bond, it breaks homolytically. One electron goes and makes a bond with the hydrogen, which also come as a result of homolytic bond cleavage. So this is how we can show. So one electron from oxygen, one electron from hydrogen meeting together in the middle, made a beautiful heart sign, right? You notice that. And another electron from here, this one that broke, this one comes back to carbon. I don't know if it's confusing, I can show on this side, carbon. And here also one electron comes onto manganese. So that is how the mechanism is working. So this is movement of one electron. So that's why we are showing half arrow or single barbed arrow. And you continue with the mechanism that is making this benzene ring keeping the same. That carbon now has a radical, meaning one electron dot, has one hydrogen still, and oxygen still attached to carbon, which in turn attached to manganese. Manganese top one picked up hydrogen, became OH, and the other one is already OH. Manganese has 1 electron. Are you getting the electron counts? Correct number of electrons. So from here, another radical mechanism is this. This electron comes from here, and oxygen to manganese sigma bond breaks homolytically. Electron comes here, makes a double bond, and other electron goes onto manganese. So if you notice, that results in, I think I can somehow accommodate the structure here. New ring and double bond. And this is the carbon. Now, as you see, it forms carbon-oxygen double bond. And it has a hydrogen, which is aldehyde group. So our aldehyde functional group has formed. Right? And manganese has become manganese hydroxide, which is the other component. Plus, you have this manganese with 2 hydroxyl group. That's that. So in the meantime, this is our cinnamaldehyde. Trans-Cinnamaldehyde. So that is the reaction you are going to be doing. So basically, you are going to reflux them together with an ether solvent and keep boiling. And when the reaction is done, you are going to do the workout. The things TA is going to walk you through how to do that. So this reaction as such is done, and it, depending on how well the reaction goes, some semester goes very well, sometimes it doesn't. I don't recall how was the situation last semester. But if you have enough time, I encourage to do another interesting thing, which is purification of this cinnamaldehyde. It may be done or may not be done tomorrow. Depends on the time to the most part, and to some extent on the TA, how confident they feel. And as I said, how much time you have. The reason for this, the product you are getting, cinnamaldehyde, structurally you see it is so close to a cinnamyl alcohol. That means your product may not be 100% pure. You may have some unreacted cinnamyl alcohol remaining with it, right? Inorganic products, those are not organic, that will be separated in your workup procedure. But these two, alcohol and aldehyde, their structure is being very similar. Number of the covalent bonds are also similar, covalent bonds, carbon oxygen in both cases, double bond versus single bond. So their polarities are also somewhat similar. Only difference is hydrogen bonding. Other than that, the molecules' polarities are similar, which means you may have some contamination of the alcohol. Alcohol meaning ceramide alcohol. So that's why it is advisable, especially when you want to do in a research lab, you certainly want to do, is to get pure, absolutely pure aldehyde. So I'm going to teach you another interesting reaction, which is chemically interesting and slightly challenging, but at the same time worth knowing. In order to get ultra pure cinnamaldehyde, let me even write the word that way, to make very pure. I think very would be enough emphasis rather than ultra. You can use not only the physical methods you have done in the past. You have purified compounds in very many ways in the past. Remember, you did distillation for liquid, crystallization for solid, but there is a chemical means, and that is fascinating. You certainly want to know that. You can do that extra purification by a chemical means, and that is going to make you an ultra pure compound. How that works? That is done by protecting the aldehyde group. So reaction is going to involve protecting the aldehyde group, because we have two competing groups. One is alcohol, primary alcohol, and aldehyde. Their polarities are somewhat similar, although not same. So if you do a chemical reaction which only reacts with the aldehyde group, that means your alcohol is going to be separated out very easily. That's the idea. So let's see how it works. I think you'll love it. So let's draw the structure of the cinnamaldehyde one more time. Here is your trans-cinnamaldehyde. Let me write the aldehyde functional group since you're showing the mechanism. The reagent you are going to be using is sodium sulfite. Sodium sulfite. Sodium sulfite. Sodium sulfite structure is this. Let me write a different color. Here is your sulfur oxygen double bond, OH, O minus. Okay, that is the sulfite structure. So basically, we are doing NaHSO3, sodium sulfite. Okay. So this is sodium ion and hydrogen. Oh, that's, I think it's, yeah, it is just sulfite. Sulfide or hydrogen sulfide? Maybe hydrogen sulfide. That's okay. We are not doing gen chem here. So what it does is this. Sulfur has a lone pair of electrons. It can attack this carbonyl carbon in a nucleophilic addition reaction mechanism that we have learned. Of course, when the sulfur gives electron, this oxygen can make a double bond with sulfur, giving you a structure that is going to look like this. Here O, oxygen is becoming O minus, carbon is dense, it has a hydrogen here, making a bond with the sulfur, one double bond here, another oxygen double bond has formed, and OH is there as such. Right? Net charge is still the same, that is our initial thing, which can then undergo a proton transfer internally. Proton moves from one oxygen to the other. Let me write as IPT. And as it does, I think you can draw the structure easily. This is going to go this and this carbon. O is becoming OH. This hydrogen stays, sulfur. Everything almost same. This is minus. Remember, we are using sodium sulfide or hydrogen sulfide. That means you have sodium ion present. Do you see, interestingly, this whole compound has turned into a sodium salt, right? And this is indeed a stable salt. A stable salt. Because you have this cation anion, a sodium salt, which also means, as you know, all sodium salts are water soluble. That means this will be separated from cinnamyl alcohol. Cinnamyl alcohol is a huge, big alcohol that is not water soluble, whereas this guy would be. So it would be easy to separate out two layers. Your aqueous layer is going to have your sodium salt, which is the salt of the original cinnamaldehyde, forming a complex with sodium hydrogen sulfide. So this complex is the salt between the aqueous layer and can be separated from non-aqueous layer, meaning getting rid of alcohol or any other organic products, because you chemically separated, made something that is only for the aldehyde functional group. And because it is a stable salt, it can be stored easily. Ideally, if you do not have time, then you stop it at this stage, because you can safely store it. You can safely store it. Close the bottle and store it there to do the next step later. So what we are doing is we are protecting the aldehyde functional group. That's why I wrote the term protecting the aldehyde group. So you can see our aldehyde group is now protected in the form of this entire salt. That is only from the aldehyde part. This here is the aldehyde part that has become this, separate from everything else. And stable salt is not stable. Yeah, I meant to say, yeah, stable. I wrote correctly, right? Not stable. Stable salt, so you can store it. So next thing remaining is to deprotect it. Right? So our structure is protected. I can even write it protected. Next step would be deprotection. Interestingly, the deprotection mechanism is very simple and easy. That is also a very one-step reaction. Involves just sodium carbonate. Okay? Sodium carbonate would be able to unprotect or deprotect this aldehyde group. Okay, so unprotect, if I say unprotect, which in this case basically meaning release. Is release a big correct word? I don't know. So unprotect. Oops. The CHO group. And instead of writing the aldehyde group, I'm just writing like this. So let's draw it separately. Instead of drawing on the same structure, since you had it saved and you are coming next week, you want to unprotect. And here is what you do. So let's draw the structure again of this protected form of this complex structure that has carbon, you have hydrogen, it has an oxygen and a hydrogen, and that has this sulfur to O minus, right? And you have sodium plus. As I said, all you need to do is add sodium carbonate, NS, Na2, right? Carbonate is 3, A2 minus, Na2CO3. What is the carbonate ion structure? Do you recall this? You learned in long time ago. Carbon with 2 oxygens are negatively charged. This is the structure of carbonate. So what it does, take a look. It's a very simple mechanism. This oxygen picks up this proton. Electrons go make a carbon oxygen double bond. And also that breaks the carbon sulfur bond. Sulfur is probably going to have to become like this. So that way you are easily, readily unprotecting the aldehyde group. Our aldehyde group is back, carbonyl is back, hydrogen is there, and rest of the thing is gone out, which is your SO3 2 minus, right? Sodium sulfite. This time it is sodium sulfite. I think originally what we wrote was sodium hydrogen sulfite. We should say sodium hydrogen sulfite or bisulfite. Right now I recall some Genchem. So do you see how a clever method, using a clever method, now we have ultra pure cinnamaldehyde. Trans, of course, trans-cinnamaldehyde. This is trans. I think you can understand it. So that would be a chemical way of getting rid of everything else, or in other words, protecting the aldehyde functional group followed by deprotection. getting ultra pure cinnamaldehyde. So that is your whole lab all about. I hope they make you do this protection on protection, because that is a good learning as far as chemistry wise, and also learning an relatively advanced tool how you can chemically purify a compound using a protecting group followed by unprotecting. If you do this, you may have to do the unprotection next week. That's why sometimes they don't let you do that. Two reasons: you may not have enough time. Secondly, next week come back, you do this unprotection. That also takes some time to purify, get a dry product, and then begin to analyze. And I think that is the reason they often skip this part. But at least I hope that you learn the method of what I explained to you. Any questions, guys? Those who are here? Any questions at all? All clear. Perfect, Danny. So very good. There is no other. You're welcome. Excellent. Anastasia. Yeah, it is straightforward. Exactly. Very good, Amira, for commenting optimistically. Yeah, perfect. All right. So yeah, follow these and all. As I said, your midterm is no surprise. Basically, everything that I have taught in these classes, all those are in some form. When there is a reaction mechanism, you want to learn that. Technical details we said, because here is when you are training yourself to be a chemist as a chemistry major. So we need to be aware of that, and we need to be prepared for that. Sounds good. So basically, I will see you next week on Tuesday, not on Monday. Tuesday, I will see you in Marshall 117. First floor. It's a beautiful classroom. Some of you may have seen that. We'll meet you guys there. All right. You are welcome. Thank you. Thank you, guys. See you. See you. Thank you. See you, everyone. All right, I'll stop recording and stop sharing.